Multivariable Calculus, Section 11.6, Curvature and Acceleration. Now let me explain right off the start that I'm not going to be developing most of these formulas because there's a ton of them, some of them much more useful than others. And the derivations are tedious and long, and I don't want to make this a 3-hour lesson. So I'm going to focus on using the formulas and mentioning which ones are easiest to use. So we'll start by talking about arc length. Here is the formula for arc length in 2 dimensions when you're given the function in parametric form. So it kind of makes sense that you would just add that third component. This is based on the distance formula in 2 dimensions and then 3 dimensions. So let me just develop this one a little bit. Here's a curve in space. If we want to know the length of that curve between these 2 points, t equal a and t equal b, we can approximate it with line segments. And the length of each line segment, using the distance formula, is the square root of the difference in the x values plus the difference in the y values plus the difference in the z values, all squared, of course. So if we wanted to approximate the length of the curve from a to b, we would add up however many line segments we had. Now if we increase the number of line segments and the number of dot points that we're joining, then we increase the accuracy of the approximation, and then if we let the number of line segments go to infinity, then we get the actual length of the curve from a to b. So this of course morphs into an integral from a to b, and the delta discrete changes in x, y, and z. The delta changes turn into instantaneous changes. But this is not in a form you can integrate. So here's the trick to rewrite it. We multiply the integrand by dt over dt, and when we bring the denominator into the square root, it becomes dt squared, and so now we have the integral that we use for arc length in 3 dimensions. So here's our formula for arc length, and your book uses an s instead of an l, and we can use the notation for that square root, the length of the velocity vector. Those are equivalent, and your book gets tired of writing that, so I'm going to do what they do and use a little v without bolding and without the arrow to indicate the length of vector v. Now we can make a function out of this instead of just individual numbers by changing that top limit to t, to a variable. And then of course we can't use t in the integrand, so we use a dummy variable du. Now what that does then is that function will give you the arc length from a to whatever, and as t increases, then that integral value will increase. And so the derivative of the arc length function, ds dt, is in fact the speed along the curve, which is the integrand, which is the length of the velocity vector, the rate of change in the arc length with respect to time. Now we're going to talk about curvature. Which of these 3 graphs is the curviest? Well, the first one is a straight line, so we say that it has 0 curvature. And for the other 2, you might think, well, duh, the third one's much curvier. Well, to the naked eye, it appears to be. But we're going to be a lot more precise than just what something looks like to the naked eye when we define curvature mathematically. Let me show you what I'm talking about. Let's say there's a car on that circle, zooming around the circle at 100 miles an hour. It's going to feel awfully curvy, much more curvy than if you just walk around it, for example. On the other hand, let's say there's a snail crawling very, very slowly around the spiral. Now which one is curviest? So you can see that curvature doesn't just depend upon how something looks, but it's also related to the speed at which you go around that curve. And those of you who drive know what I'm talking about. So curvature is the rate of change in direction with respect to the distance traveled. And mathematically speaking, what we're going to do is we're going to start with what we call the tangent vector, which is a unit vector in the same direction as the velocity vector. So we take the velocity vector and divide by its length. So it looks something like that. And the curvature then is going to be defined as the rate of change in the tangent vector with respect to the curve length. So it's how quickly is your direction, the tangent vector, changing with respect to how far you've gone. And that's the precise mathematical definition of curvature. So I'm going to use this little k to represent curvature. I couldn't find exactly the same letter that they used in the book. In 2 dimensions, here's our handy-dandy formula. In 3 dimensions, one possible formula is the reciprocal of the length of the velocity vector times the length of the derivative of the tangent vector with respect to t. But that's usually very messy, so instead I prefer this formula for curvature, which is the length of the cross product of the velocity vector with the acceleration vector over the length of the velocity vector cubed. Now if you just have a plain old function, then that top formula morphs, because you can think of x as being t then, f of x, f of t for y. And so the derivative of x becomes 1 and the second derivative of x becomes 0. So that top formula morphs into this formula. Normal vectors. A normal vector is a unit vector, denoted n, such that n is perpendicular to the tangent vector and points into the concavity of the curve, because as you'll recall, there's 2 possibilities for a perpendicular vector, and we want the one that points inward to be our normal. Now it turns out that the rate of change in the tangent vector with respect to arc length is equal to the curvature times the normal vector. I just mentioned this in passing because this is actually not a very useful formula, since it's really difficult to get tangent t in terms of arc length in the first place. So we'll use this formula. It turns out the acceleration vector can be broken into component-wise into these 2 perpendicular vectors t and n, and the coefficients or components are a sub t and a sub n respectively. And we have formulas for a sub t and a sub n that aren't too terrible. The dot product over the length of the velocity vector for a sub t, and the length of the cross product of velocity and acceleration divided by the length of the velocity vector for a sub n. And so those are actually easier to find than n in 3 dimensions. And so we're going to use this formula to compute the normal vector. Acceleration vector minus the tangential component times the tangent vector divided by the normal component. Now you don't have to go through this in 2D. 2D is much easier, because in 2D we just need to find, if we've got the tangent vector, we just need to find a normal vector such that the dot product would be 0. So if the tangent vector has components a and b, all you've got to do is switch them and negate one of them, and then your dot product will be 0. And you just choose the appropriate n so that it points into the concavity. One last topic, the oscillating circle. At each point along a curve, there's a circle tangent to the curve at that point. And the curvier the curve is, then the smaller that circle is. And so it turns out that the radius of that oscillating circle then is the reciprocal of the curvature. And so now we're going to look at some examples of all these different topics. Number 6, compute the arc length of the curve defined by these parametric equations from t equals 0 to t equals 1. So there's our handy-dandy formula, and the various derivatives are easy to compute. We square them in our formula. And at this point, feel free to use your calculator to evaluate the integral. However, this one I happened to notice was a perfect square. Then the square root and the square cancel. Everything is positive, so I don't have to worry about absolute value. This is easy to integrate. Throw the 1 and the 0 in, and we can have an exact answer, or if you prefer, an approximate decimal answer. Number 10, compute the curvature at t equal 2 given these parametric equations. So this is a 2-dimensional problem. And so we use our 2-dimensional parametric formula for curvature. And the derivative of x is 1, the derivative of y is 2t plus 3, and then the second derivative of x is 0, and the second derivative of y is 2. And then we square the first derivatives in our formula for the length of the velocity vector. So then we put 2 in for t and do a little bit of arithmetic and a little bit of simplification, And if you prefer, you can have a decimal approximation. Now notice that the graph of this is a parabola, and so the only part where it's curvy at all would be near the vertex. And then as you go on up the parabola, it gets straighter and straighter, but never completely straight, never a straight line. And so the curvature is never going to be 0, but it's going to get very, very small as you follow the parabola. Number 14, compute the point of maximum curvature for the graph of y equal log x. So here's a picture of the natural log, and its curvy is somewhere in the middle here, and then gets less and less curvy out on the branches. So here's our formula for just a regular old function for the curvature. And the first derivative is 1 over x. That goes in the denominator under the square root. And the second derivative is negative 1 over x squared. So then to simplify that, I multiplied by x cubed over x cubed. When in the denominator, that can then go inside the parentheses as an x, and then inside the square root as an x squared. And it simplifies to this. Notice that x is always positive, so again we can drop the absolute value. Now to take the derivative, I rewrote it as a product, and then took the derivative of x times the second factor, and then x times the derivative of the second factor using the chain rule. To simplify that, the easiest way is to factor out an x squared plus 1 to the negative 5 halves, and then change that into a fraction. And then when will the original formula for curvature be maximized? Well, when the derivative is 0, and there's only 2 solutions, one of which is extraneous because in this problem x is always positive. Therefore, the point of greatest curvature is when x is 1 over root 2, y is a log of 1 over root 2, which can be rewritten by taking 2 to the negative 1/2 and bringing that negative 1/2 in front of the logarithm. And so there's our point where the graph is curviest. Number 20, compute the tangent vector and the normal vector at pi over 2 given this two-dimensional parametric curve. So here's a picture. Notice that the point when t is pi over 2, x is pi over 2 minus 1, and y is 1 minus 0. Here's our formula for the tangent vector. And so the two derivatives for x and y are 1 minus cosine and positive sine, and then we square those to get the length of the velocity vector. And then we put in pi over 2 for t, and we get this vector. Now, since we're in 2 dimensions, we want the normal vector so that the dot product is 0. And so all we have to do is switch the numbers and negate one, and the numbers are the same. So to choose the correct one, notice that in the normal vector, the change in y is downward. So the change in y is negative. So it's the j component we want to negate. And there's our normal vector at pi over 2. Number 30. Find the equation for the oscillating circle for y equals e to the x at the point 0, 1. So here's a picture. Now a few things to note is remember that the radius of the oscillating circle is 1 over the curvature. And notice that the tangent line at e to the x has a slope of 1. And that means that the angle is 45 degrees. So if I draw a line parallel to the x-axis up here at our point, that angle will also be 45 degrees. And we're going to need that a little later. So here's our formula in just a regular function for the curvature. Notice that y prime and y double prime are both e to the x. And so then if we put 0 in for x, we get 1 over root 2 cubed. So our radius then is the reciprocal of that, or 2 root 2. Now to get the center of the circle, we drop a perpendicular from the radius, which is a length of 2 root 2. And because of that 45 degree angle, then we can use the Pythagorean theorem to easily compute the legs of those two, of that right triangle. And so our center point then is 2 units to the left, so the x-coordinate is negative 2. And then we're already up 1 unit, and we have to go 2 more units, so the y value at the center would be 3. So now we can use our center point and our radius to write our equation of the circle. Number 34. Compute the curvature function for r of t equal t, t squared, t cubed. Well, here's one possible formula, but as you'll see, the tangent vector function is too messy to take the derivative of, so we're going to use this one instead. Alright, so the velocity vector is 1, 2t, 3t squared, and the acceleration vector then is the derivative of the velocity vector, 0, 2, 6t. So to do our cross product, I won't belabor this too much. We have to make our determinant, copy the first two columns, and then we multiply downward to get that vector, and we multiply upward and get that vector, and then the final answer for the cross product is the bottom minus the top. So there's the cross product. So we want the length of the cross product, which simplifies to that radical, times 2. And then we want to divide that by the length of the velocity vector cubed. So it's square root cubed, or you can rewrite that as 3/2. Okay, now 42 relates to 32. It's the same vector valued function, but they want the tangent vector and the normal vector, which gets really messy. So I'm really glad that they gave us a value to plug in. So here's our formula for the tangent vector, the velocity vector divided by its own length. There's the velocity vector again, and there's the length of the velocity vector. And if we put 1 in for t, then we get this answer. Now for the normal vector, we're going to use this formula. So before we can compute it, we need the formulas for a sub t and a sub n. And here are v and a again, just to review. We did the cross product on the previous page. So there we have the length of the cross product divided by the length of the velocity vector. And then the dot product is just 1 times 0 plus 2t times 2 plus 3t squared times 6t, all over the length of the velocity vector again. And so the normal vector, take a deep breath, is the acceleration vector minus the tangential component times the tangent vector, all divided by the normal component. Now, I wouldn't want to have to simplify that algebraically, so luckily we're going to plug in 1 for t. There it is again, and there it is with the 1 plugged in. And that's still kind of messy. So to simplify, let's multiply by 14 over 14, and then let's reduce by 2, and then we do our multiplication and addition, and there's the normal vector at 1. Okay, so now it's your turn. Try not to scream too much. I will warn you that these problems are tedious. Be careful. Maybe you should work with someone else so you can catch each other's errors. And try not to wake the rest of the family when you are working on these problems.